Welcome to GiulioBursiOptics, your channel for non-imaging tutorials. Today we are going to talk about the skew. So we'll start from the limits of the CPC, we'll move on to the skew invariant, and then we'll see what happens when you break the symmetry of the system. Did you ever get a lower efficiency in your system than what was expected? Today we'll discuss one of the possible causes. We begin our analysis from the compound parabolic concentrator we looked at in the last video. Our source is collimated, so let us say it is the sun, and the rays fall within the acceptance angle of the reflector. Some of them strike the base directly, where we assume the receiver or the sensor sits, while those that meet the sidewall are reflecting down into the exit aperture, exactly as designed. Now let me switch on one more ray. Although it is parallel to all the others, it strikes the reflector, is reflected, and fails to reach the termination at the bottom and is instead reflected back out. How is that possible when the acceptance angle is being respected? It happens because we are in the third dimension. Until now, we have quite reasonably analyzed the problem in two, when we discussed et and u, and when we discussed the edge rays. And working in two dimensions is a standard way to begin an analysis. It is what is done every time, which also means that when the third dimension is introduced, some problems tend to appear. This ray is not collected by our concentrator because its skew value is higher than what the concentrator is able to accept. So what is this skew quantity? It tells us how tilted a ray is with respect to the axis of the system. We call it h, and we compute it as the product of three terms: the refractive index of the medium the ray is traveling in, multiplied by s, multiplied by the sine of theta. Theta is the angle between the ray and the optical axis, while s is the minimum distance between the ray and the optical axis. Not the distance at a given point, but the smallest distance the ray reaches along its path. There is a conservation property attached to this quantity. In a rotationally symmetric system, h is an invariant, which is why it is called the skew invariant. What that means in practice is that there is a region the ray can never enter because its minimum distance from the axis is fixed. Let us look at it through another example. Here is a reflective tube, where I have set the walls as reflective, and I will switch on a single ray. This ray has a certain angle with respect to the axis, and therefore a certain skew value, and as it reflects off the wall, it traces out this pattern. It becomes very clear how the repeated reflection of the single ray draws out a sort of forbidden cylinder, a region inside the tube that the ray never enters. That forbidden region follows directly from the skew invariant, and it exists only because the system is rotationally symmetric. This is the important part. Rotational symmetry is extremely widespread as a starting point. If the symmetry is what creates the invariant, then the obvious question is what happens when we take it away on purpose. So, I have built a set of light pipes, all of the same length and the same inscribed radius, differing only in the shape of their cross-section, and I will send the same ray into each one of them. If we switch on the ray in each of these, some fairly interesting thing happen. All the rays have the same origin, off-center, and the same angle with respect to the base. In the hexagon, some structure survives. There is no central forbidden region anymore, but the ray still traces something that repeats. With the octagon, we get this crossed weave thing, which carries a certain irregularity within. if we move to the last two instead, the 7-sided section and the geared one, the reflection become apparently random. Any periodic structure is lost. So the choice of section governs how much periodic structure survives, and the sections that share no simple relationship with a reflection pattern are the ones that destroy it most completely. So where is the problem? Designing a light guide with a section of this kind, with a very large number of facets, brings several difficulties. There is the practical question of how it would actually be manufactured, and there is the fact that we end up with great many reflection angles that are potentially awkward or hard to control. If the component works by total internal reflection, we will have a very large number of reflections of the walls, with a progressive loss of intensity as a result. If we now return to our concentrator, we have seen that even when the attendue of the source and of the receiver appear to be compatible, the skew content of the source rays may not be compatible with the skew of the receiver or the system. The skew content of the source rays may not be compatible with the skew that the receiver or the system is able to accept. These are two parameters that have to be analyzed carefully and separately. Attendue is useful for a first assessment of whether the system can work at all, a minimum condition, so to speak, while the analysis of the skew is more involved because it says something far more precise about how the source actually behaves. I wanted to spend a little time on the TR collimator and see what happens when we move the source from the origin of the lens. So we start from the usual 2D projection. The lens is rotosymmetric and the rays all lay on the meridional plane. Okay, we see that the ray do not exit from the plane, of course. So what happens if we move the source, in this case along the x-axis? Let's try. So let's say, for example, we move it 4 millimeters. Okay, let's trace again. We see the rays start from the plane. In this case, the center of the fan is directed along the z-axis, but as soon as they reflect or refract, they leave the plane. Okay, as you can see, they tend to go inward with respect to the axis of the lens. What happens instead if the center of the fan is tilted a bit? So let's try to move this one this way. Okay. As we can see, as the rays get this caustic on this plane, on the other one we have the crossing of the rays instead of being collimated. Okay, it's a sort of 3D caustic. What happens instead if the rays goes the other way around? So toward the external part of the lens. In this case, there is no caustic, no plane, and the rays create this sort of light cone, so to say. We have seen that the inclination of the rays in the two directions, inward and outward with respect to the lens, have two very different behaviors. So it's quite interesting. To conclude, the rays we begin the analysis with the ones lying on the plane that contains the axis, serve to give a first impression of how the system works. The refinement then has to be carried out properly by looking at the genuine three-dimensionality of both the source and the optical system, because the two cannot be considered in isolation from one another. Thank you and see you in the next video.